So my name is Sandy, and I'm here to talk to you about orchestrating software-defined assets with Dagster. Some quick background on myself. If you've heard me speak at a data conference before, it was probably a long time ago, in my Cloudera days, when I was contributing to Hadoop and Spark and co-wrote this book about data science. I spent the middle chunk of my career as a practicing data scientist, building pipelines and machine learning models at a couple different companies, which was a fun time, but also a frustrating time, because I found that there were big gaps in the tooling that I needed to do my job. So a couple of years ago, I came back to the world of data tooling to try to fill what I saw as the biggest gap. And I joined the Elementl team to work on Dagster. But before we get to that gap, and before we get to Dagster, I'd like to step away from the world of data entirely and talk about front-end engineering and cluster orchestration and DevOps. These domains have something in common, which is that they've all gone through a big transition in the last decade or two. So we used to build websites using jQuery, but now we use React. We used to orchestrate our compute clusters using Yarn or Mesos, but now we use Kubernetes. And we used to provision infrastructure using high-powered shell scripts, but now we use Terraform. So technology transitions happen all the time. But what's interesting here is that all these transitions have something in common, which is that they move from an imperative paradigm to a declarative paradigm. For those of you who aren't familiar with these terms, here are some crude definitions. So under an imperative paradigm, you give commands telling your system what to do. Change this, change that. With the declarative paradigm, you describe the end state that you want your system to be in, and then you let a control plane manage change. So what's going on here? Why do we see this pattern of change? If you take a closer look at the history of any of these software domains, you start to get a sense of it. So the initial challenge is about speed to build stuff. It takes developers a long time to get basic things done, like provision an EC2 server or change what shows up in a text box. Tools come along that speed this up dramatically. So for example, jQuery makes it stupidly easy to change what shows up in the text box. By making it so easy to build stuff, these tools solve the initial problem, but they create another one, which is that now people build a lot of stuff. It becomes difficult to reason about all this stuff. What text boxes are expected to appear on the page? And what text are those boxes expected to contain? So finally, new tools arrive to tackle this problem, and these new tools are built declaratively instead of imperatively. That's because declarative tools are highly effective at taming complexity. They do this in a couple main ways. So first, they ask users to explicitly state their intentions and expectations, which means you get an unambiguous plan that's inspectable by anyone. Second, they provide a principled way of managing change. Instead of an unstructured logs of things that you did, you can ask the system, why did you make this change? Why did you put this value inside this text box? And the system can give you a clear answer. So now let's talk about a domain with complexity and change up the wazoo, and that domain is data. In the world of data, where are we on this tooling journey? Well, it used to be very hard to build stuff. 10 years ago, if you wanted to calculate some statistic over every event on your website, you needed to set up a compute cluster with 20 different services, and even the simplest operations could take tens of minutes to complete. Since then, we've built powerful databases and data processing engines that make this all effortless. So now with Snowflake or Spark, you can write 3 lines of code and get a result in a couple of seconds. And we've built workflow managers that allow you to easily chain a bunch of data processing steps together. Building data pipelines has never been easier. The result is that we build tons of data pipelines. So even at medium-sized organizations, it's not uncommon to have hundreds of tables, machine learning models, and data sets, and tens of thousands of lines of code that are responsible for generating them. This code typically spans different compute frameworks and storage systems. So some will happen in a data warehouse, some in Spark, some in Snowflake, Pandas, TensorFlow, etc. Here's a little example from my past life working with health insurance data. To answer a simple question like, how many people were admitted to the hospital during this time period, we ended up with a chain of intermediate data sets, which spanned 3 compute frameworks. So there's a lot that's great about this picture. Maintaining intermediate data sets lets us reuse valuable data cleaning work. And supporting multiple ways of processing data gives us the flexibility to use the right tool for the job. But without extremely careful shepherding, this complexity naturally devolves into chaos. We end up with multiple versions of the same things, created by different people or even by the same people at different times. It's hard to distinguish trustworthy, maintained data from one-off artifacts that went stale months ago. Discovering how a table or machine learning model is generated often requires a heroic act of code spelunking. And debugging requires untangling a complicated history of state mutations. This chaos interferes with our ability to accomplish our goals. We can't trust our data because we don't know how it's generated or how it's expected to be kept up to date. And we spend most of our energy wading through our existing system, so we don't have the mental space to expand it. Which is all to say that I think we're solidly in this upper right box. Managing all the data in pipelines is still really hard. What would it take to bring a declarative approach to data management and tame this chaos? So a declarative approach fundamentally revolves around the declarative entity. In front-end engineering, the entity is a UI component. You declare the UI components that you want to exist and how you want them to be rendered. In DevOps, it's a resource. You declare the servers or other infrastructure components that you want to exist and what you want their properties to be. So what's the declarative entity for data? It's the asset. An asset is a database table, a machine learning model, a report, any object produced by your data platform that captures some understanding of the world. It could be a source asset that's ingested directly from some external system. It could be a derived asset that's built from source assets or other derived assets. Creating and maintaining data assets is the main reason that people build data pipelines in the first place. Assets function as the interfaces between different teams. They're the objects that we inspect when we want to debug problems. And they're ultimately the products that data teams build for the rest of the world. Managing assets declaratively means defining them in software. It means writing code to specify the set of assets that you expect to exist and how you expect those assets to relate to each other. An orchestrator then becomes responsible for keeping the contents of physical storage aligned with those definitions. Materialization is the word we use for a physical manifestation of an asset. For example, an actual table in a database or file in a file system. If this all sounds a little bit abstract, that's fine. I'm going to spend the rest of this talk making this concrete and walking through the implications. And I'm going to do that through the lens of Dagster. So for those of you who aren't familiar, Dagster is an open source orchestration platform. We recently introduced software-defined assets as a core element of Dagster's data model. With this new abstraction, Dagster becomes a critical tool not just for running workflows, but also for organizing, managing, and evolving data. A software-defined asset specifies an asset that you intend to exist, as well as how to compute that asset's contents. Assets don't come out of nowhere. They're produced by computations, which in Dagster we call ops. To get a table in your data warehouse, you normally have to run some code that puts it there. And those computations normally operate on other assets. So a software-defined asset is basically the combination of these three things. It has an asset key, which identifies the asset that it corresponds to. For example, the name of a table in a database or the path to a file in a file system. It has an op, which is the function that can be run to produce the asset. It has upstream asset keys, which reference assets that we supply as inputs to the op that we use to compute our asset. And these upstream asset keys usually correspond to asset keys of other software-defined assets, which means that a group of software-defined assets naturally forms a graph. Here's a software-defined asset that's built using Dagster's Python API. The name of the decorated function defines the asset key. So in this case, the asset represents a forecast of activity on some website. The implementation of the decorated function is the op. So in this case, it uses pandas, but ops can use any compute framework. And then asset doesn't even need to be tabular data. For example, it could be a machine learning model or a set of images. The arguments to this function designate the upstream assets that this asset is based on. In this case, it's an asset called activity daily stats, which holds historical data on our website's activity. Something you might notice here is that I'm not showing any code that actually reads or writes to or from physical storage. The op is a pure function. To support this functional style of programming, Dagster allows the code that writes an asset to storage to be provided separately and shared by multiple assets. It's not a requirement to do it that way, but it's preferred because it makes assets more testable. But decorating a Python function isn't the only way to build a software-defined asset. So if you want to define an asset using SQL, a DBT model actually fits all the criteria that we talked about for a software-defined asset. Let's walk through one. This activity daily stats asset has the same core components as the Python asset. The name of the file, which determines the name of the DBT model, is the asset key. The select statement is the op. It's what we run to compute the contents of the asset. And the refs are upstream asset keys. They point to assets that this computation depends on. Dagster can actually model dependencies between assets defined in Python and assets defined in DBT. It does this by offering a Python utility that makes it easy to load all the models in a DBT project as software-defined assets. Once you define a set of assets in code, either directly in Python or by loading them from an external tool, you can start working with them in Dagster's web UI. So here's how you tell Dagster to scan a Python package and make all the assets inside of it loadable from the web UI. And here's that web UI. We have a visual representation of all the assets that we were just looking at in code. This is all open source, by the way. You can get to this view by pip installing a package and running a single command. So at the bottom, we've got our activity forecast asset, which is the one that we defined in Python. Right above that, we've got the activity daily stats asset, which is the one that we defined using DBT. And above that, we've got a couple other assets which came from models in our DBT project. If you've worked with tools that show DAGs, this might look a little familiar. But there are a couple of key differences off the bat that I'd like to point out. So the first is that each node represents an asset, not a task or op. In fact, multiple assets can be generated by the same op. These 3 DBT assets are generated by the same runDBT op, which invokes the DBT command line tool. The second is that there's no central DAG artifact that holds the dependency structure. Each asset on its own knows about the upstream assets that it depends on. This makes it scalable to large numbers of assets. You don't need a central team to maintain a code artifact that captures all of them. So here, we're looking at just the assets that I showed you the definitions of. But we've also got links to assets that these assets depend on, but that are loaded by Dagster separately. So at this point, all we're looking at here is a set of asset definitions. They correspond to code in our Git repo, not artifacts in physical storage. That is, they have no associated materializations. But Dagster doesn't just track asset definitions. It also allows you to materialize assets and tracks those materializations. So we can click this button on the upper right to materialize all the assets that are shown here. That launches a run, which contains a log of everything that happens as we execute the computations that materialize these assets. When the run is complete, each asset now has a materialization. That is, it now exists in persistent storage, and Dagster knows about that and when it arrived there. Dagster knows some other useful stuff as well, and if we dive into one of these assets, we can see it. Here's the page for an individual asset, our activity forecast asset that we defined in Python. It contains details about the asset and its history of materializations. A materialization isn't just a record saying that a computation ran. It's a description of the object that was produced by the computation. Dagster lets users plug in code that records runtime metadata about the asset that's being materialized. So, for example, we've recorded a few things about this materialization. We've recorded the number of rows, the file system path where it's stored, a sample of the data, and the set of columns and their data types. This asset-focused view is especially valuable when you shift to the perspective of someone who depends on an asset. So let's imagine that we're in our BI tool. We're using this asset to try to understand what the future holds for our website. We notice something fishy. Maybe some of the data that we expect to be there is missing. So we can pull up this search box in Dagster, type in the asset that we care about, and get to the asset page that we were looking at before. From that page, we have all this information about the asset, its materializations, its dependencies, its metadata at our fingertips. And if we have permissions, we can directly launch a run to rematerialize the asset and patch up the issue. So to summarize what we just saw there, software-defined assets provide a layer above our physical storage that allows us to express what assets we expect to exist and how those assets are produced. The software-defined asset graph is based on assets defined in code. which means that practices for managing and evolving code can be harnessed for managing data. We can launch runs to materialize our assets, which means computing their contents and writing those contents to physical storage. By focusing our tooling on assets instead of tasks, it becomes easy to get visibility into what has happened with the assets that we care about. So we define some assets and materialize them, which is cool, but it's not enough. And it's not enough because assets are constantly changing. New upstream data is constantly arriving, and we're constantly changing the code that derives our assets from that upstream data. The result is that our asset materializations naturally drift from their definitions over time. When that drift occurs, we need to launch computations to bring those materializations in line with our definitions. And launching computations at the right time is typically the job of an orchestrator. Traditionally, orchestrators are systems that are responsible for a few things. They invoke computations at the right time, they model the dependencies between computations, and they track what computations ran. This makes orchestrators the natural experts on a few topics. They know when stuff happens, they know when stuff is going to happen, and they know what it takes to make something happen. And because they're experts on these things, they hold the key to answering some of the most important questions that we end up having about our assets. So for example, is this asset up to date? What do I need to run to refresh this asset? What code and data were used to generate this asset? After pushing a change, what assets need to be updated? When will this asset be updated next? But if you try to pose these questions to a traditional orchestrator, you'll immediately run into the issue they have no idea what an asset is. They can tell you what tasks have completed, what tasks are meant to run after each other, but not about how any of that has to do with the assets that these tasks are reading and writing. They're ill-equipped to answer these questions because asset is not central to their data model. If we could conceive of orchestration in a way that's centered on assets, we'd have an extremely powerful set of tools for managing and understanding them. So we talked about the job of a traditional orchestrator. The job of an asset orchestrator is a little different. It's to manage change in data assets. Dagster supports two approaches to orchestration for assets. The first one looks very similar to how scheduling works in traditional orchestrators, except that it focuses on assets instead of tasks. You can select a set of assets to be rematerialized at some regular cadence, or via a sensor based on arbitrary logic. The second one fully leans into the declarative approach. You tell your orchestrator to launch computations that resolve discrepancies between your asset definitions and their materializations in storage. So let's start with the one on the left as a way to get our feet wet. This code tells Dagster to run a job every day at midnight, and that job materializes a subset of the assets in our asset graph. So it targets assets, not tasks. Here's what this scheduled job looks like in Dagster's UI. So up on the top here, we can see when it's going to run. And the job includes just the assets that we've selected. We can still see the data lineage between the assets inside the job and the assets outside the job. Putting the schedule on the asset instead of on a task makes it easy for stakeholders to answer questions about when assets will be updated next. When they navigate to the page for an asset, they can see the frequency that it's going to be updated at. So just by framing scheduling in terms of assets instead of tasks, the orchestrator becomes an ideal system for answering these questions that we looked at earlier. It eliminates the friction of translating between assets and tasks, and it can speak authoritatively about how assets will be updated as time passes. So that gets us pretty far, but fully realizing the benefits of a declarative approach requires going farther, to an orchestration approach that's based on reconciliation. Here's how it works. First, we observe discrepancies between how the world is and how the world should be. Then we launch computations that are required to make those two match. The most basic discrepancy in need of reconciliation is when you have a software-defined asset with no materializations. To make the set of assets in physical storage match the set of assets you've declared, you need to materialize the asset. A related discrepancy is when you're working with a partitioned asset and only some of its partitions have materializations. Another discrepancy is when the contents of an asset don't reflect the contents of the upstream assets that it depends on. So if the most recent materialization of the asset occurred earlier than the most recent materialization of the upstream asset, then it's likely that the asset's contents are stale. Dagster raises this discrepancy with an upstream changed indicator. A fourth discrepancy is when the metadata on an asset definition doesn't match the metadata from its latest materialization. So here's an asset whose definition includes metadata describing the set of columns that it's expected to contain. Every time we materialize the asset, we record the columns that were included in the materialization. If the asset is fully reconciled, then these two lists of columns should match. But in the case up here, they don't match. The definition includes a column that the latest materialization does not. So we need to take some action. So we need to take some action in this case to resolve them. The reconciliation approach can be more involved because it requires thinking about all the different ways that an asset's materializations can stray from its definition. But it has a few big draws. So instead of trying to keep track in your head of when assets have drifted from their materializations, you delegate that bookkeeping to the orchestrator. You can avoid unnecessary computation. So why recompute an asset if nothing about its inputs have changed? And you get a rationale for why computation happened. For example, we rematerialized the asset X because the columns it had no longer matched the columns that we expected it to have. So at this point, I think we have this understanding of the fundamentals of software-defined assets and how we manage change inside of them. And with that out of the way, I'd like to talk a little bit about how software-defined assets fit into the context of what's happened in the world of data in the last couple of years. If you ask 20 people for definitions of the modern data stack, you'll get at least 20 different answers. But here's a fairly bland one that I think at least isn't going to ruffle too many feathers and will work for our purposes. The modern data stack is a set of tools and practices that have dramatically simplified common patterns for working with data. At least in part, I think that the modern data stack owes its success to an embrace of declarative principles. For example, in the past, to build a derived table, you would write an Airflow task that issues a create table statement to your database. Nowadays, you're more likely to define the table directly as a DBT model. In the past, if you wanted to ingest the table into your data warehouse from your production database, you would write an Airflow task that executes a sync. Nowadays, you're more likely to just tell Fivetran or Airbyte or Meltano that you want that table to exist in your warehouse. With these declarative approaches, you get all the declarative benefits that we discussed earlier. So it's understandable why they're attractive and why we're moving in this direction. But there's something that's lost as well. And to understand it, we need to go back in time and take a look at the pre-modern world. In the pre-modern world, you'd use an imperative orchestrator like Airflow to invoke computations across a variety of frameworks. As we covered earlier, there are a lot of problems with this world. Having an imperative orchestration layer fosters a lot of chaos and forces you to constantly translate between the world of assets and the world of tasks. But there's also some important bathwater that we shouldn't throw out with the baby here. This centralized orchestration layer makes it easy to understand everything that's running in one place and to make sure that everything is running in the right order, even across tools. In the world of the modern data stack, purpose-built tools for each of the verticals essentially roll their own orchestrators. So each of the tools shown here, except Python, which we'll get to in a minute, offers its own way to schedule work and view the assets that are defined inside of it. I think this loss of a central control plane is a regression. The lack of a shared orchestration layer results in an operationally fragile data platform. When dependencies cross tool boundaries, for example, when the tables that you derive via DBT depend on tables that are synced from a production database, it becomes difficult to get a coherent view of what's going on. So when dealing with this situation, a common pattern is to try to time the schedules so that the syncs will complete before the derived tables are rebuilt. But this is pretty brittle. If the syncs take longer than expected, there's an overlap in the timing, and then the derived tables will get rebuilt using stale data. So it's easy to lose track of what ran, what's supposed to ran, and whether things ran in the right order. And you might also notice that Python has largely been left behind in this picture. By focusing on specialty tools that simplify common data patterns, we risk losing our ability to run generalized computation when we need it. So we're forced to choose between A, a unified approach that's stuck in an imperative paradigm, or B, a declarative approach without a unified control plane. I don't think there's any fundamental reason we need this trade-off. We can have a declarative asset-based orchestrator that supports polyglot compute. Dagster allows delegating computation and asset definitions to external tools, like DBT and Airbyte, while maintaining a unified control plane over all of them. That control plane is declarative. You don't lose sight of the assets you're working with when you schedule them in your orchestrator. And it makes Python a native citizen of the modern data stack. Python asset definitions can coexist alongside DBT models, etc. So here's an Dagster asset definition graph that spans Python, DBT, and Airbyte. The three assets at the top are tables that are populated via Airbyte 6. Materializing them via Dagster, for example, clicking on that button when we're on the asset page for one of them, results in a call to Airbyte to run the sinks. The assets in the middle, with the orange tags, are DBT models. Materializing them in Dagster, clicking on the button on the asset page, results in a call to DBT, either CLI, RBC server, or DBT cloud. And the asset with a light blue tag on the lower right is an asset that's computed using Python downstream of one of these DBT models. So that brings us to the end of our journey. Let's boil it down to the main things that we talked about. The world of data needs a new spanning abstraction, which is the software-defined asset. A software-defined asset is a declaration in code of an asset that should exist and how to compute it. Defining assets in software enables a new way of managing data that makes it easier to trust, easier to organize, and easier to change. The seat of the asset definition is the orchestrator. The system that you use to manage change should have assets as its primary abstraction and is in the best position to act as their source of truth. When it comes to the modern data stack, software-defined assets allow Python to become a first-class citizen. And asset-based orchestration offers a unified control plane without sacrificing a declarative approach. So thank you very much. I'd love to answer any questions you have in my office hours, which I believe are immediately after lunch.